You know, it's something we never really think about. But how does your laptop, in a room full of other computers, know exactly which one is the printer? It's not magic. Not at all. It's actually a detective story, a little mystery that plays out millions of times a second inside our networks. And today, we're going to be the ones to crack the case. So here's our plan of attack. First, we'll look at the fundamental problem, the network's address problem. Then we'll meet our lead detective, a protocol called ARP, and see exactly how it works. After that, we'll investigate a really interesting character, an imposter known as proxy ARP. Then we'll see how the network gets smarter over time. And finally, you get to put on the detective hat and test what you've learned. Okay, so right at the heart of this whole mystery is a case of dual identity. See, every single device on a network, your phone, your laptop, your smart TV, is juggling two different addresses at the exact same time. And for any of them to talk to each other, the network has to figure out how these two identities are connected. Let's think about it like this for a second. You have a name, right? It's what people call you. But you also have a fingerprint, which is completely unique to you and can never change. Your name could change, people might call you by a nickname, but that fingerprint, that's physically part of who you are. Well, it's the exact same deal for devices on a network. On one side, you've got the IP address. Think of this as the name. It's a logical address. It's kind of like your home address. It tells other devices on the internet where you are. And just like your home address, your IP address can change. When you take your laptop from your house to a coffee shop, you get a new IP address. But then, on the other side, you've got the MAC address. This is the fingerprint. It's a physical address, a unique serial number that's literally burned into the device's hardware when it's made. It never changes. It identifies exactly who that device is, physically. And right here, this is the core of our mystery. For two devices on the same local network, like your computer and your printer at home, to actually talk, they need to know each other's physical MAC address. The IP address gets the data to the right neighborhood, sure, but it's the MAC address that's needed to deliver it to the right doorstep. The network has the name, but it desperately needs the fingerprint. So how does it get it? Well, this is where our hero steps in. The protocol that plays detective and solves this whole identity crisis is called the Address Resolution Protocol, or as we'll call it from now on, ARP. So the official definition says ARP's job is to map that high-level logical IP address to the low-level physical MAC address. But really, it's the translator. It's the bridge between where you are on the network and who you are on the network. Super, super important. So how does this detective actually work? Well, it's a really simple but totally clever four-step process. Just imagine you're in a big open-plan office. In step 1, your computer, let's call it host A, needs to talk to a coworker. It knows their name, their IP address, but has no idea where they sit. So it stands up and broadcasts, basically shouting to the entire office, "Hey, who has the IP address 130234325?" Now, in step 2, everyone in the office hears this, but only one computer, host B, goes, "Oh, hey, that's me." Everyone else, they just ignore the shout and get back to work. And this leads to step 3, the reply. Host B is smart. It doesn't stand up and shout back to the whole office. That would just create more noise. Instead, it replies privately directly to host A and says, "That's me. Here's my MAC address, my exact desk location." And finally, step 4, the connection is made. Host A has the fingerprint it needs, and it can now send its message directly to host B without bothering anyone else. Simple, right? Okay, so let's translate that office analogy into the real language of the network. Now, this diagram might look a little technical, but don't worry, it's just showing us the exact structure of those shouts and replies we were just talking about. These are the actual data packets. On the top, you've got the ARP request, that's the shout, and below it is the ARP reply, the private answer. Let's zoom in on the most important detail here. Let's focus on the two most critical parts of this conversation. In the request packet, when the sending computer shouts, "Look at the destination address," it's a special address made up of all Fs. This address is the universal signal for everyone. You can think of it like the to all in a company email. It guarantees that every single device on that local network gets the message. Now look at the reply packet. The computer that's responding does not use the all Fs address. Instead, it sends its reply directly to the specific MAC address of the computer that asked the question. This is what we call a unicast, a direct one-to-one message. So the whole process is incredibly efficient. One public question gets one private answer. Okay, so now we know the basic rules of ARP, but let's look at a really fascinating situation where the network actually cleverly breaks those rules for a good reason. This is called proxy ARP. And honestly, the best way to think of it is as a helpful receptionist for the network. So the problem that proxy ARP solves is this. What happens when a computer sends out that ARP broadcast, that shout, because it thinks it's looking for a local device, but the device it wants is actually on a totally separate network? Normally, that request would just go unanswered, and the connection would fail. And this diagram shows that exact scenario perfectly. We've got network A on one side and network B on the other. Now, notice the important part. They both use the same IP address range, 10.10.1. something. This is what causes the confusion. Because the neighborhood part of the address looks the same, a computer on network A is tricked into thinking a computer on network B is right there on the same local street. But they're not. They are physically separate, only connected by that router in the middle. A normal ARP broadcast, our shout, simply cannot cross that router. It's like shouting in one building and expecting someone in the building across the street to hear you. So what does our helpful receptionist, the proxy ARP router, do? Well, it's always listening to those ARP shouts. And when it hears a request for a device that it knows is on the other side of that divide, it steps in. Instead of letting the shout just disappear into nothing, the router intercepts it and replies to the sender, basically pretending to be the computer they were looking for. So let's just walk through this little deception step by step. A computer sends out its ARP shout, looking for what it assumes is a local friend. The proxy ARP router sees this request and knows the real destination is actually remote. So what does it do? The router replies with its own MAC address. The original computer is completely fooled. It now thinks the router's physical address belongs to the computer it wants to talk to. So it sends its data packet right to the router. The router then catches that packet and acts like a middleman, forwarding it across the boundary to the actual destination. It's a pretty clever trick, right? Which is why you'll sometimes hear it called an ARP hack. So this process of shouting and replying works, but it can be really inefficient. I mean, imagine if every single time you wanted to talk to your coworker, you had to stand up and shout their name across the office first. It would get super noisy and it would slow everything down. A good detective doesn't resolve the same exact case from scratch every 5 minutes. They keep notes. And the network, well, it needs to do the same thing. It needs to build a case file. It just wouldn't make any sense, right? It'd be a huge waste of time and energy to solve the same case again and again. A smart detective remembers the clues and the conclusions from their last investigation. And our network detective, ARP, is no different. It needs a memory. And that memory is called the ARP cache. It's brilliant. Every time ARP successfully figures out an IP to MAC address mapping, it stores that little fact in a small temporary memory table. So the next time the device needs to contact that same IP address, it doesn't shout, it just quietly checks its own notes first, finds the answer, and sends the data straight away. This makes the whole network way faster and much, much quieter. So what's actually inside this case file? Well, obviously it stores the IP to MAC mapping, but look at that timeout value. This is really, really important. Devices can leave the network, or maybe their IP address changes. This timer acts like an expiration date on the information. It ensures that old entries get automatically deleted after a few minutes. This forces the device to occasionally send out a fresh ARP request, just to double-check and make sure its information is still accurate. It keeps the network up to date. All right, you've seen how devices get their identities, you've met our detective ARP, and you know how it keeps a case file to be more efficient. So now, it's your turn. Let's put on the detective hat and see if we can solve a couple real-world network problems using what we've learned. Okay, here's your first assignment. I want you to think back to that ARP shout to everyone in the office. What is the specific, universal destination address that a computer uses at the physical hardware level to make absolutely sure every single device on the local network hears its request? And the correct answer is, of course, C, FFF. This sequence of all Fs is the universal MAC address for a broadcast. Now, you might have seen an IP broadcast address before, like 255.255.255.255. That works at a higher, logical level, what we call layer 3. But for the physical hardware itself, the switches that connect all the cables, to understand that a message is for everybody, it has to be sent to this all Fs physical address. It's the official signal at layer 2 for a public announcement. Okay, detective, time to break out the calculator. This is a real-world question about network performance. Imagine you have a local network, a LAN, with 100 computers on it. If every single one of those computers sends out an ARP request once every 10 seconds, how much total traffic is that generating on your network every single second?
Let's solve this case one step at a time. First, step 1, let's find the rate for a single computer. We know each one sends one request every 10 seconds. So to find the rate per second, we just do 1 divided by 10, which gives us 0.1 requests per second for each host. Easy enough. Next, step 2, find the total rate for the whole network. We have 100 hosts, and we know each one is generating 0.1 requests per second. So we multiply 100 hosts by 0.1, and that tells us there are 10 total ARP requests happening across the entire network every single second. Finally, step 3, let's calculate the total amount of data. We're told each request packet is 64 bytes. We have 10 of those every second. So we multiply 10 by 64, and that gives us our final answer, 640 bytes per second. Now, that might not sound like a lot, but it's a constant stream of background noise, a baseline of traffic that's always there, just from devices trying to find each other.
So there you have it. We have cracked the case of local communication. We now know that ARP is the network detective that allows all the devices in the same room to find each other using their unique fingerprints. But here's the catch. This whole process, this shouting and replying, only works on a local network. And that leaves us with a final, much bigger mystery. How in the world does your computer find a server that's thousands of miles away on the other side of the planet? What protocol plays detective when the shout is just too far to be heard? Well, that's a case for another time.